Today my topic is I want to talk about the key ideas of STIR, and we compare to Fry. Compared to Fry, STIR has lower query complexity. And how does it achieve that? The answer is in his name. STIR is stand for shift to improve rate. This is STIR. So the answer is shift to improve rate. Let's see how does it achieve that? Okay, we know that if Fry and STIR they both solve the Reed-Solomon proximity problem, testing problems. It is from IOPP. It means that we have a function f. We have a function f, and the prover, and this is the verifier. The verifier query first prover send something, and the verifier query, and then the prover send something query. At the end, the verifier should decide two cases. First, if f is a code word from D, and he will accept. He's happy, and he will accept. And if he decides that f is far from RS code, more than delta, and he will reject. This is the IOPP protocol, and at the end, the verifier will this he will accept, and this he will reject. So Fry and STIR are both IOPP, and let's compare Fry and STIR to say his key ideas. For function f, we and a code word FL. This means this is the field. This is the evaluation domain. And this is the degree D. This means it contains all functions f. His evaluation on the L, and he is at the L. He is consistent with a polynomial f hat L, and f hat is a polynomial. This is a function, and this degree is less than D, structurally less than D. So we want to compute this rate. It is the degree over the size of evaluation domain. We can suppose it is n. So this is the rate. Under the rate means that a function his real message his real message over if the rate is lower, and the redundancy of the code word will increase, and the wildfire will be more easy to define this, which he defined f which is that. So the complexity he will this means that the query complexity will be lower. So I will first write. Okay. I present FRI protocol. This is approver and this is verifier. First, first verifier will send alpha randomness, and he will use this to fold. Let's see it. G is LK from F. It will, K is the folding factor, and alpha 1, and he will set G2, and this is LK2 F, and then and so let's LK means XK X L. So and the FRI is the STIR is different. And the STIR, this is STIR. So he will send back G prime. Also, he used the same alpha 0. So he will L prime F. But this L prime's size is N over 2 is and the degree of G prime is also okay. I wrote this. The degree is also k-fold. The fold function is the same as the FRI. So so the degree of so this is a verifier will check that is a code word from F L prime D over K, right? Okay. So this is G2 prime L plus F. So this verifier will check that G2 prime is a code word from F L prime D over K square. And but the FRI, the verifier will check G1. G1 is a code word from IS F L K D over K. This is RS F L K square D over K square. So we can compute FRI's right, and this rate. Let's do some compute. Okay, FRI rate. Rho is equal to. So in the I step, it will check that if F, if G GI is a code word from FLKI D over KI, right? So this rho I, it is this degree over the size of that. So it's right. So this is D over Ki, and this is N L over Ki. So it is equal to D over L. So it is equal to the rho from the first and the STIR. STIR is his rate. We should verify. Should check that Gi prime is from this. Let's see, Li D over Ki. So his rate is this degree over his size is equal to D over Ki. But the third is different. Is that this is equal to L over 2 to I. So this is key. Right, I'm right. 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 So when this term is when K is larger than 2, this is less than 1, right? So the rate of STIR will be lower, right? So this is the K idea that he has less rate, so he has more redundancy of the code word, and so the query complexity will be lower. Okay, and we can. Is that clear? Okay. Okay. And we can compute the query complexity of fry and STIR. If we it remains that you have a round by round error, round by round soundness. It means that in every round you have to the soundness error should be for example 2 to minus lambda. Lambda is a security parameters. So every round you should get this security, and if you want to get this security, you can query Ti times. So every round we say Ti round to get that security parameter. So the whole complexity of the query is if we have m round, so the whole is that. We have two conclusions. First is the query complexity of fry. Query complexity. Okay, it is O lambda times log D minus log rho, and the STIR is O minus log plus. So we can see that in STIR it is log. The my term is log, but the fry is log. So so it has lower query complexity. And in the paper, they run the experiment, and the STIR is about too fast than fry. Okay, yeah, this is the okay idea. Have any question?
Is this one because the field extension you get this?
A field extension?
How this equals to this one?
Oh, because in the fry, we fold this. We use K to fold F, right? So this is xk. For example, L equals to omega 0, omega 1, omega 7, and in the fry, for example, K equals to 4, and in the next round, LK will be. He used this to 4 to map omega 0, omega no, map omega 0, this 4 omega 3 to get omega 4, right? So the size will be, so the size LK will be L to 4, right? Yeah. This is the fry, it is the same. Right? So this is, right, okay.